Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up where I left off last time involving graphs. So in my previous lecture, I had defined what a graph is, but I'm going to remind you just of a couple of things that are relevant for our discussions here. So I've talked about a variety of different kinds of graphs. I talked about so-called undirected graphs, directed graphs, and mixed graphs. And I've talked about different edge kinds, like directed edges, undirected edges. I'm going to focus mostly on building up some more terminology today. Then I'm hoping that we'll talk about how we could represent a graph on a computer. And also I'm hoping that we'll start talking about some algorithms for solving problems on graphs. Because as I mentioned last day, graphs are this powerful way we can model many problems, but they themselves, graphs, are very fascinating in their own right. So I must stress that graphs are not only just a tool for modeling problems, they also have many applications in all sorts of disciplines. So graphs can be viewed as networks. You can put them in all sorts of different places. As I said the other day, that if there's likely a problem out there, there might be a way to model it as a graph. So it's not just simply that I have my problem and it formulated as a graph. You may have a problem out there that's very natural to talk about in terms of graph theoretic concepts. So this is like another way you could talk about problem solving, is now we could talk about also graphs as another structure to describe them on. And many problems that you probably will ever encounter in practice, many of them can be modeled quite naturally with graphs. So we'll see that in the upcoming lectures. So anyways, I want to talk more about concepts here. So recall that a graph consists of vertices and edges. So for example, here's an undirected graph. It has undirected edges. And we talked about the other day about adjacency. For example, I would say that vertex 1 and vertex 6 are adjacent to one another. Also, I could talk about incidence. So suppose I give you an edge here. I could say that this edge is incident on vertex 6 and vertex 1. So anyways, let's talk a little bit about, first I'm going to talk about paths and cycles. So for some problems, for example, routing-based problems, or even just general concepts, knowing what a path is, or what some people call a walk, is fairly important to be aware of. So what's a path? It is simply a sequence of adjacent vertices. So we call the path simple. So I must stress that some people call what I've defined here as a path a walk. So just be very wary of the graph theoretic terminology some people are using. So I'm just referring to a path just as a sequence of vertices. And in some colloquial circles, people will sometimes also infer that paths have to be so-called simple. So I'll refer to a path, if I need it to be simple, I'll call it a simple path. What does it mean to be simple? It just simply means that all the vertices are distinct in the path. So just to give you an example of what I mean. So if I had this graph here, suppose I started off at vertex, let's start at vertex 2. Suppose I start at vertex 2. I'm going to go for a little walk. I'm going to go to vertex 2. I'm going to go to vertex 3. Then vertex 1, then vertex 4, then go to vertex 5. So I have vertex 2, and then I go to vertex 3, then vertex 1, vertex 4, and then vertex 5. So this is a path from vertex 2 to vertex 5. A question, is this a simple path? So in this case, it is a simple path because no vertex is being repeated. Now in contrast, if I were to give a different path, suppose I give this one with, for some reason my markers were kind of conjoined like that. If I did another path, say if I start from 7, and I go to 2, then go to 1, then back up to 7, then go to 6, and then go to 5. So that would be a path, say, it would be vertex 7, the vertex 2, vertex 1, then back to vertex 7, then to vertex 6, and then vertex 5. Sorry, I'm sort of running out of space on this right side. So the one in red here, is this a simple path? Nah, it's definitely not. It repeats vertex 7. So one thing I should point out about simple paths is that as a consequence of their definition, because every vertex is not repeated, it also means that the edges don't repeat either in the path. So some people will list paths in terms of their edges, some will list them in terms of their vertices, like I've done here. So one thing I want to remark is if I give you a directed graph, remember those are graphs that consist of directed edges. What it simply means is that you have to follow the arrows in the path. So for example, if I had directed arrows around the outer perimeter of this graph, say they're all directed like this, clockwise around the graph, for example, and say all these other ones are directing out from V1. I could only go in this direction if I were to talk about a path from V7 here. I would only be able to follow the arrows in the paths. I can't go backwards on an arrow. So that's what a directed path is. So the path has to follow all in the same direction. So you have to follow the arrows. So a cycle, in contrast, so first, are there any questions about what a path is? So all it is just a sequence of adjacent vertices. You could list them in terms of their edges. You could also list them in terms of their vertices, or both. Because once you understand what a path is, a cycle's dead simple. Okay, so a cycle is just simply going to be a sequence of adjacent vertices, just like a path, except what's going to happen is that the start and end of the path have to be at the same vertex. So for example, if I were to start at, say, vertex 1, and I go to vertex 3, then go to vertex 4, then come back to vertex 1, so I go vertex 1 to vertex 3 to vertex 4, then back to vertex 1. This is an example of a cycle. So that's what a cycle is. So it's just a closed path. So I go for a little stroll, then I come back to where I started, okay? That's all a cycle is. And naturally, you could also define what is called a simple cycle by just simply requiring that all the vertices have to be distinct, just like when I defined what a simple path is. So one thing also to note is if you want a directed cycle, same idea as a directed path, except the start and the end have to be the same vertex. Same idea. Is the idea of a cycle pretty straightforward? It's just that you go on a little trip, you have to come back to yourself. That's all it is. Now, wonderful, wonderful. So that's one key concept I really want to make sure you're aware of, because we're going to see cases where we want to compute paths in graphs. Now, another notion I want to talk about is connectivity. So sometimes I would like to know if there's some relationship some vertex or this graph has. So for example, when I compute paths, it might be nice to know that I could reach every vertex in the graph, for example. So one natural way to talk about this is so-called a graph being connected. So a graph G is connected if there exists a path from each vertex to every other vertex. So what do I mean by this? So if I pick any one vertex in here, if I pick any other vertex, say I pick vertex 7, I pick vertex 4, there has to exist at least one path that gets me from vertex 7 to vertex 4. For example, I could just take a walk through vertex 1 to get to vertex 4. I could go all the way around like this. So there's at least a couple different ways I can get there, right? And to be connected means that I could put my fingers on any two vertices like this, any two of them, and I could find a path to them from one to the other. So that's what connected means. So are there any questions about the definition of connected? Because I'm just going to elaborate on one more specialized version of it. Sorry, I'm getting very excited here. So we'll mostly be playing around with this idea of connected. But I feel like I need to make the remark for directed graphs, because we talked about undirected graphs and directed graphs. Connected is a broader notion. For directed graphs, there's two notions. There's something called weakly connected and strongly connected. So what is weakly connected? It's just simply the same definition as connected, except you're going to take every directed edge in the graph. You're going to then replace those with undirected edges. So for example, if this was the directed graph, say for example, that had, say the one that I talked about actually just a moment ago. Say if I take all these edges and I make them all go around like this. Actually, let's make it even, yeah, let's do this. Let's do this. So I make all these edges so they're directed out like this. So if I wanted to ask if this graph is weakly connected, what I would do is I would ignore the arrows on the edges, and I would just say, I'm just going to treat them like they're undirected edges, and I ask the question, is it connected? If the answer is yes, then that directed graph is weakly connected. In contrast, strongly connected is the truest of being connected on a directed graph. This is where you literally pick up my definition again, but you treat it, the definition where I have, if there exists a path, you replace a path with directed path. So for example, I have a question for you. Is this graph strongly connected? So just to give you an idea what I mean. So for example, if I pick vertex 7, I could get to vertex 2 by following the arrows here, from vertex 7 to vertex 2. Likewise, I could get to vertex 4 by following this path, by following the arrows, vertex 7 to vertex 2 to vertex 3 to vertex 4. Now, the question, is it strongly connected though? So can I pick any two vertices in this graph? So I can pick any arbitrary two of them. So notice here that if, for example, if I wanted to take a path from, if I were to say if I wanted to go from V6, and I want to go, okay, I want a path from V6 to V1. Am I able to do that? No, right? So this graph would not be strongly connected. So in this case, you would have to consider all the pairs and see if there's a path from there to there. But yeah, no. So that's just the notion of, but yeah, I've sort of gated off vertex 1 from all the other ones. So, that being said, are there any questions about connectivity? It's really just simply about paths and the existence between two vertices, a path. So in this case, in the just more general case, this is the one that we're going to be mostly familiar with. The other two I just felt like I just need to acknowledge. So in terms of concepts, I'll be mostly focusing on just this definition, just the graph being connected or not being connected. Not so much this one. I feel like I just wanted to acknowledge it because sometimes you run into directed graphs and I want to make sure you know that there's these stronger notions of connectedness. But yeah, it's all just about finding paths. So I put my finger on any two vertices, I should be able to find a path. But I must always stress, just make sure you look carefully at whatever definition they're using for paths. Like I said, the order they take the pairs in might matter. Sometimes they just ignore it. So for example, they'll say, okay, well, a path from V6 to V1. They might say, okay, well, is there a path from V1 to V6? Obviously, in this case, I could get away with that, right? I could just simply pick V1 and I could just take it the other way around. But that doesn't make sense in our definition, right? Because that's not a directed path. That's going backwards in our definition. But yeah. So, are we okay with this? Give me 2 thumbs up if we're okay with this. Because I want to talk about a concept that you're familiar with, just I'm going to get it out. I'm going to make it broader than even what we've talked about. So, if we're okay with that, let's head over there. I'm going to kind of boogie on over here. So, yeah, this is a very poor excuse for boogieing, by the way. So let's talk about trees. So we've talked about trees, and I'm sure you've seen trees plenty upon plenty of times, right? But I'm just going to talk about them more broadly than even before. So this is going to be rather brief because I know that you've seen plenty about trees, and I'm sure you've had this topic sort of beaten into you enough times that I think that you might well be like, okay, I've seen a lot about trees already. So anyways, I'm going to give you a broader definition of a tree. So first, just as a note, for example, when you see binary trees and all of these, we've defined these all on so-called rooted graphs. Rooted trees. So rooted trees, that's where I designate a special vertex, and then we have a root for it, and then we describe some relationship it has with the other nodes or vertices in the graph. So what's a tree more broadly? It's just simply a connected undirected graph that has m is equal to n minus 1 edges. So remember, m is the number of edges, n is the number of vertices. So you might ask, Dan, I may have heard of trees before, but that may not be the definition I've been given before. So a tree has to be connected, and it has exactly n-1 edges. So there's a few different equivalent ways. These aren't even all of them. There's like, I could give you like a list of maybe at least 6 other, instead of 3, I could potentially give you up to 6. There's many equivalent definitions for trees. Sometimes it's useful to pull out one of these definitions and show it to your friends. Every once in a blue moon in a proof that involves trees, you'll see somebody poke out one of these definitions and say, hey, look, a tree has this property because it's part of its definition. They'll oftentimes use one of these definitions to get away with that. So there's a few other ways I could define them. So for example, if I take any 2 vertices in the graph, there has to exist a unique simple path between those 2 vertices. So what do I mean by that? For example here, if I look at my tree I have right here, this is just a tree. I didn't put any labels or anything on it. It's just unlabeled. If I pick this vertex, there's a unique path that gets me from this vertex to that one. There do not exist 2 or more of them. There always exists exactly 1. So that's one way you could define a tree. This is sometimes very helpful in terms of being a definition. But keep in mind, you can take my definition and you can try to use it to prove these other ones. You can actually take some of these and chain them together to prove that, oh, this one is the same as one of these other ones. Then I have that other one, and then I can use that to define the other one. Prove that it's equivalent to the other one, and so on. You can chain them together in like a pretty neat cycle of sorts, which is kind of weird. But it's pretty epic, especially for those that like the mayonnaise. It's a nice way you can chain together equivalent definitions of proofs. You can often chain the definitions together through logical proofs. It's really nice. But anyways, that's one of them. The other one is that if the graph is connected, but if I were to attempt to remove an edge from this graph, the resulting, what we would call an induced graph, is just the result of that operation. It just simply means that if I remove any edge in that graph, it becomes disconnected, meaning it's not connected. That means that there's going to be one vertex that's just going to be isolated, or at least one vertex that's isolated away from the other vertices. So for example, if I were to get rid of this edge right here, this edge would be all by itself, all sat over there, right? So that would mean that that's one property of a tree that's really helpful to know about. But you can actually define it this way as well. So as long as it's connected, but if you were to attempt to remove any one edge, it would disconnect the graph, meaning that there's at least one vertex that's totally isolated. In fact, some vertices that are called this, so for example, I have some trees over here. Some people refer to these, when I just have a single vertex just hiding away where nobody else can get to it, something they call these isolated vertices, or an isolated vertex. Why? Because it's all by itself. I don't know. Maybe it just wants to take the day off. I'm not quite sure. But that's another way. Another way is just simply that the graph is acyclic, and the exact number of edges it has is n-1. So acyclic just simply means it contains no cycles. So you cannot find a single cycle in it. So one neat property, and keep in mind there is another way of characterizing a tree using what I have in this note here, is that if I give you a tree, if I attempt to add any new edge to it, it actually creates a cycle. So for example, notice that if I were to attempt to put an edge right here on this tree, it would create a cycle like this. In fact, one way you can actually prove that this property is true, you just simply take this characterization of a tree, the one that says that there are unique simple paths. Well, there exists a unique simple path from its 2 endpoints here of the cycle. Of this path here. If I add this one edge in here, I can form the cycle by just simply going through that unique pathway and then going across the extra edge. It's kind of neat like that. That's why some of these definitions can be rather helpful. But yeah, so just keep in mind this property. We're going to use it at some point later on in this course. Is that if I attempt to add any one edge, you'll create a cycle if I give you a tree. So just to give you a picture, you know what a tree looks like, right? This is just a general tree, right? It has exactly n-1 edges. Now, in terms of terminology, there's also this notion of a forest. So a forest is simply a collection of trees. And for any forest, it has the property that the number of edges is at most the number of vertices less 1. So instead of it being an equality, it's actually an inequality. So for example, here's a forest. It has 1, 2, 3 trees. And that's a forest. Is that kind of neat? Are there any questions about this? I think that it's pretty natural. But if you have any questions or need clarifications, don't hesitate to bug me about this stuff. I'm laying out some terminology for us. So if we're okay with this, give me 2 thumbs up. Okay, good. I have to make sure I go through these things because once the natural question is, okay, so if I want to start talking about different problems, it'll become very natural for me to have to define things to talk about those problems. If I lay out this general graph terminology, then it'll be easier for us to talk about it without having to lay out a whole bunch of definitions every single time. This is why we're actually going through this terminology right now, so that you have some familiarity with some key graph theoretic concepts, because those will only be beneficial if you want to study more computational problems, because many computational problems can be defined on graphs. And the other thing is that it saves us a little bit of time later on. So that being said, let's talk a little bit about, we're going to talk about the notion of a subgraph. So we talked about what a graph is, but I haven't described what a subgraph is. So let's talk about what a subgraph is. So it's simply a subset of vertices. So I'll show you an example of this in a moment. So if you're not sure about the word subset, I'll explain. I know that those taking like 310, they know what what subset means. A subset of vertices, and edges that forms a graph H. So suppose I give you this example of a graph. This is a rather nice graph. I like this graph. So I'm going to draw it out. So I'm going to draw some edges. So I got the outer perimeter covered. Just going to draw these a little bit bigger. That way you can clearly see the vertices. Okay, so one last bit of piece I'm going to add in here. I'm just going to... There we go. There we go. So here's a graph here. I assure you I'm not trying to summon the occult here. Though, if there anything weird happens, you could blame me, okay? So anyways, if I have this graph, one thing I can do is I can take some subset of the vertices. Yes, it's a star, exactly. Exactly. I remember when I was a kid, kids would always draw these doodling stars in their notebooks. I'm not sure how popular that is these days, but it's always fun to do. But now, so I can take any collection, any subset of the vertices, and I could pick off edges as long as they can form a graph. Because obviously I can't have it where I take this edge and I don't take both of its endpoints. So for example, a subgraph of this one, which is simply the star. I could just take the star. So this example, so this would be a graph G, and here's a subgraph H. So I just pick off some of the vertices. I could take some of the edges. I'm not required to take all of the edges that are incident on them. It's any subgraph, meaning it's a subset of the vertices and edges. As long as it forms a graph, we call it a subgraph. Okay? So I would say that H is a subgraph of G. Now, if you're not convinced by this, just simply transpose this, just like take this and just slide it on top of here. Now, I must stress, remember, like I said, the picture of the graph isn't really that important for us, at least at this context. In some areas of graph theory, sometimes the drawing of the graph is rather important. Here, we just care about the structure of the graph, right? How the edges relate with the vertices. So it doesn't have to look like that. I could make some really bizarre looking picture that isn't the star. So anyways, let's talk briefly about one other concept. Is this concept called a connected component. So let's talk about a connected component. So I warn you in advance, this definition will first come off rather technical and jargon sounding, but I'll elaborate on what it means. So it is simply a maximally connected subgraph. So first, there's a lot of things going on with this definition. First, we know what a connected graph is, right? We know what a subgraph is. So it's some subset of the vertices and edges, but there's this one part called the maximally part that isn't really quite clear, right? I need to explain what I mean by this. So just to give you an example, actually first, just make it kind of clear what I mean by this. Suppose I give you this graph here. So if I want to talk about a maximally connected subgraph, now remember a subgraph is simply going to be some subset of the vertices and edges. Now, if I want to make the graph the connected component, if I want to make the subgraph include as much of the graph as possible, that's what I mean by maximally. So for example, if I were to exclude this edge here, and if I were to not to include that, you'd agree with me that everything is still connected, right, in this graph? It still remains connected. But you notice that I could still put it back in, and it still remains connected, right? Now, what I would like to have happen is that I include as much of the graph as possible, such that if I were to try to remove any vital part of it, the graph may become disconnected. I want to make the piece of this graph as big as possible. So just to give you an example of what I mean by this. So suppose I have a graph that looks like this. So I'm just keeping this a little high level for us because for us, we just care about knowing what a connected component is. We're not going to be working too intimately with connected components, but I know that in some application areas, you do encounter this idea of connected components. So suppose I give you a graph that looks like this. I know my vertices there are a little out of scale sometimes. So notice here that I have, it looks like 3 pieces, right? There's 3 parts here. This is all one graph. So a question for you, is this graph connected or disconnected? So just think back to the definition. Is there a path from this vertex, say, to this one? No, right? It's disconnected. So that means that there's going to be more than one chunk of the graph, and I would like to know how many chunks there are. And so now you might actually ask, I'll ask you right now. So you might ask how many connected components there are. There's actually exactly 3 connected components here. So for example, here there are 3. Now, question, if I give you a connected graph, how many connected components does it have? How many does it? It just has 1. It just has 1, that's it. Why? Because of what I just said a moment ago, right? I include as much of the subgraph as possible when I come up with my connected component. I explore as much of it as I can, but notice that in this case, if it's connected, there's not going to be anything sitting out over here that I can't reach, right? So connected graph, so just as another example, every connected graph has 1 connected component, namely itself, right? But yeah, now are any questions about connected component? Does this seem pretty clear? Just think about it in terms of how big of a piece can I make of the graph by imagining if I could explore as much of the graph as possible. And then you end up with these chunks. Those chunks are what we call the connected components. So I have 3 connected components. Each one, by the way, this is where the name comes from. It says connected component. Notice that each one of these is connected. So each subgraph here is connected, as the definition would say, and there's as much of the graph there as possible, right? Seems pretty natural once it's all kind of spliced together like that, right? Okay, so any last questions about connected components? Because I want to now talk about how we could represent graphs on computers, because that's going to be one of those natural things we would like to have, especially when we start talking about algorithms that we can use to solve graph problems or problems on graphs. So if we're okay with this, I'm going to move over there, and we're going to start talking about how we can represent a graph on a computer. So that's one very, it's kind of important for us because right now graphs are kind of this really, I don't know the best way I could describe it. They're just kind of sitting out there in the ether. You can draw them out on pieces of paper and stuff, but I would like some systematic way of me describing them in terms of how I can represent them. Just in the same vein as you may have talked about with like, oh, I want to represent a collection of elements for any other data structure. So I want to do the same thing with a graph. So let's talk about representations of a graph. So I'm going to highlight 2 here for us, but there do exist more than just these ones, just to be very clear. If you always find yourself curious about those, I can always tell you about those afterwards or something like that. I'm just going to highlight 2 of the more popular ones that they often are very natural to talk about in terms of graph algorithms. So there are several different ways to represent a graph. That's a little squeaky. There are several ways to represent a graph. So I'm going to show you 2 general schemes. For each one, I'm going to show you a classic way of implementing it, and then I'm going to show you a much more generalized way. So for example, if you don't really like the limitations of the classic representation, say if you want something more object-oriented, you may find the other one a little bit more appealing. So both are useful in their own right. So I'd just like to show you both of them. And that's not even just about usefulness, it's just showing you how you could represent them. So each will have a classic. So the classic version is just going to be a very tight, concise, and efficient way of representing the data structure. The other one is going to be more general, more verbose for flexibility. So if you want to do something more object-oriented, it allows for much more flexibility for how you can play around with it. So if you want to swap out one of the data structures with a different one, that's the idea. So for example, if you want to switch out some part of it for a different data structure, it's built to be suitable to do this. So if you want to use like a hash table for some part of this, you can do that. You can do all sorts of things like that with the latter version. So each will have a classic version and a generalized OO version, so more of an object-oriented version. Keep in mind that the classic version also can be completely OO based. It's just, like I said, very concise and simple. I'll highlight and mostly focus on the classic one, but I'll show you what the generalized one looks like so you can get a flavor for it. So the first type I want to talk about is an adjacency matrix. So this is one that's rather natural. This is one of the first things that you might think of trying to do to represent a graph. So what I could do is I have a 2-dimensional array, or matrix, a 2D array. Okay, I'm just getting rid of the A here. That's a little bit weird. A 2-dimensional array A, where each element of a references if two vertices are adjacent or not. It's a little squeaky. If the squeak, by the way, if ever annoys you, let me know, okay? I'll switch to a different marker. Are adjacent or not. So I'm going to first show you the kind of classic way of approaching this. Then I'm going to show you the much more general one, okay? So I must stress that it stores. So I'll show you a much more general scheme for this thing when you want to have weights in the graph, like distances or costs. But I'll start with just the most basic stuff that we've been looking at here so far. So it stores zeros and ones, where if I look at a position A sub I sub j, if it equals 1, this implies that edge ij is in the graph. So if that's the case, then of course, naturally, otherwise, A sub I sub j equals 0 means ij, the edge ij, is not in the graph. So we're going to be encoding this matrix or two-dimensional array or table as just simply a bunch of ones and zeros. And each one of the ones and zeros, based on how I read the number, like the column number and the row number, it will tell me if there is that edge in the graph or not. So there's some lovely properties this will have, which I'm going to highlight in a moment. But let me just, one thing else I need to point out here that you may not have noticed right away is that I labeled the edges with the numbers that are in the square brackets, right? So you'll notice that in my examples, I've had all sorts of different labels I used for the vertices, sometimes even having none. So one thing I should point out is that I will typically presume when I talk about the adjacency matrix that there is some way for me to label all the vertices starting from, say, 0 up to n minus 1 if n is the number of vertices. So just keep that in the back of your mind when I'm doing this, okay? So just to be formal about this a little bit, that is, so just to summarize what I just wrote, A sub I sub j is going to be equal to 1 if the edge ij is in the set of edges, and 0 if the edge with the endpoints I and j is not in the set of edges. So we're going to do an example just to show you what I mean by this. So let's talk about that. So first, is this definition clear to everybody? Is that I'm going to have it where I'm going to have a 2D array. It's going to be filled with ones and zeros. And each position is going to tell me if there's an edge in the graph or not. So you'll see when I get to the example, there's going to be a nice property that certain graphs have. So just going to head over here. Let's do an example so I could actually show you what one of these would look like. Because you know how to make a 2D array, right? So it's a very natural and simple way of implementing a graph. You just make a two-dimensional array and you fill in the ones and zeros to represent what your graph is. So I've got to show you how that's exact, like just show you a proper example of what this would look like. So let's do an example. So suppose I have a graph like this. Say if I have it V0, V4, V3, V1, and V2. And I'm going to connect V2 to V1. So these are V2 and V1 are adjacent. V1, V3 are adjacent, and V2, V3 are adjacent. I'm going to label the edges too to make it easier for us to see what's going on. So I'm going to add labels to these edges just to make it a little easier for us to see what's going on here. D and E. Okay. So based on so first, this is the graph I'm going to look at. And let me write out the classic version first so that you can see how this would. So I'll refer to this colloquially as classic version. So if you see it on the assignment, I tell you, oh, draw me what the adjacency matrix looks like in its classic version. This is what I'm referring to. So one thing I need to point out is that, so let's first write out what that matrix or 2D array might look like. So one thing I want to point out is that I'm going to presume that there's a way I can index each one of the vertices. So I'm just going to use the subscripts of the vertices just to label them. So normally when you implement this, you'll either have some set of objects that each will be looked up in some table that tell you what index it is, or you just simply implicitly just label each one of the vertices as a number starting from 0 up to n-1. Usually the latter is very common. That's why I use these subscripts. It's just to show you that as long as they're labeled in a way that's very natural, where it starts at 0 up to n-1, because I have 5 vertices here, you'll notice I have rows and columns, 0, 1, 2, 3, 4. Now, notice that I'm going to go through each one of the entries. I'm going to put in zeros and ones to fill in for each one of the spots. Now, so for example, if I start in the first row, which is row 0 and column 0, is there an edge that goes from vertex 0 to itself? No, right? There isn't. In fact, there are none for any one of the vertices, right? So you know right away that you should put zeros in all along the diagonal of this matrix. Just zeros all the way down the diagonal. For any simple graph, this would be true. So you know right away you're going to have a diagonal. So now I'm going to look at vertex 0. Notice I only have one edge here, and it's the only one that the vertex it's adjacent to is vertex 4. So you know right away that there's going to be a 1 right here, and all the rest of these are just zeros in the first row. Now, you can always spin this another way, but I'll come to that in a moment. If I look at vertex 1, notice that I have 2 edges that are incident on vertex 1, D and E, which connect me to this other endpoint, vertex 2 and vertex 3. So notice that I have from vertex 2 to vertex 3, but I don't have one to vertex 0, so I know that's a 0. And I have 2 and 3 here, 2, 3, and then naturally I don't have any other ones, right? So I could keep doing this process, right? Now, I have an interesting question for you. Okay, this graph is undirected. So one thing I want to notice here is, if I were to ask a similar question that I did while I was filling in these rows, if I look at a column and ask, okay, is vertex 0 adjacent to vertex 1? Would I get a different answer at all? As I would if I asked if vertex 0 was adjacent to vertex 1 in this way? So looking at a column, then the row, or versus a row and then a column? Would it make any difference for an undirected graph? Yes, an excellent observation. So notice that the way we would describe this in terms of matrices is that this matrix is actually going to be symmetric. So if I look at the diagonal, if I read everything in this diagonal, I look at everything on the so-called upper triangle, if I flip it like this and I mirror it over this, everything that's on here will be right here. That's true for any undirected graph, especially one in our case here. So all I have to do is I could just literally just copy my rows down as columns. So I could just go, so I have a 1 here because notice I'm flipping it like this. And likewise, I have another. So notice so if I ask the same question, if I have vertex 2, is it adjacent to vertex 1? The answer is yes. Likewise with 3, but none for 4. And I could keep doing this, right? And eventually I end up getting 1, 0, 1. And then I have 1, 0, 1 like this. And this is my adjacency matrix. So anyway, so do you see how you could do this on an actual computer? You just simply make a 2D array and you just assign each one of the positions. So this, for example, if you have some input data that reads off the rows of the adjacency matrix, you can see how you could do with some basic I/O and build the actual graph in terms of a 2D array, right? So this is fairly concrete, but also fairly simple to pull out. I have a question for you. If I made the graph directed as opposed to undirected, would this matrix be symmetric or not? Could I copy all of these like this if it's a directed graph? No, I can't guarantee that, because remember like it mentioned here, if I were to have an arrow that goes from, say, if I have a directed edge from V1 to V2, but not one from V2 to V1, that would only appear on one side of the diagonal, but not on the other one. So, wonderful, wonderful. So I'm going to show you now the more generalized version. So I'll refer to it as the generalized version. So typically when I talk about and ask and test you on things, I'll usually refer to the classic one, almost always. But I feel like I want to show you kind of the OO version you can use as well, because sometimes you like to manipulate edge objects and other things of this sort. So let me just show you the same thing, just as in its generalized form. So what I do is instead of storing zeros and ones, I store null or nil. I'm going to use nil, but it doesn't really make much of a difference. Still a null pointer. I'm going to have null pointers for any entries that are not are going to represent there's an edge not there. Whenever there's an edge that is there, I'm going to include a pointer or reference to the edge object. So, for example, if I do the same thing again, so if I'm just labeling the rows and columns just to make it easier for us to transcribe, but it's absolutely not necessary. So like labeling these doesn't matter. It's just something I'm doing to make it a little easier for us to read. So wherever I had a 0 there, I'm just going to put nil, which I'm just using as an abbreviation for null pointer or null. And wherever where there's a 1 here, I would store a pointer or reference to the edge object. So in this case, notice that I have zeros adjacent to 4 here. So that means that, notice that there's an edge A there. So I would store a reference or pointer to edge object A. So when you're building this, you'd create edge objects and you would have it where you hang on to this reference to the edge object and you assign it to that entry. So if I go through this whole thing, I'll end up with nil. Actually, would it be easier if I just put an N here just for your purposes? I'll just fill in the rest with N's, like capital N, just because I notice my nils are starting to bleed into each other. So let me just put them as N's, but all of them will be nil wherever I have a capital N. So I would have D, then E, then nil or null. Then I have null, D, null, C, null. Then I have null, E, C, because remember it's all symmetric. In fact, I could just fill in this diagonal here just fine. And I have B, B, null, null, and A. So notice that I would just, if it writes something long enough, it starts looking like a word. It went in the microwave, okay? I apologize. I put in the microwave a little too long. So notice that all I've done is I'm just storing the references to edge objects as opposed to ones and zeros. So I just store null or the reference to the edge object. So this is a generalized way you could play around with adjacency matrices, but this one's perfectly fine too if you have some way of looking up that data. But you'll find if you want direct access to those edge objects, this is also rather helpful. But yeah, no, so just remember that when I play around with this, that the vertices are assumed to be labeled 0 to n minus 1, or n is the number of vertices. Just keep that in mind. But yeah, that's that's an adjacency matrix. It seems rather grounded, right? So I want to talk about some properties of adjacency matrices that I want you to just be aware of. I'm going to highlight some of them. If there's more things I want to talk about, I'll refer to them to you in the notes. I also want to highlight just a couple of pros and cons, okay? So the first thing you should notice is that the space usage here. So if I want to use an adjacency matrix, if I want to talk about it in terms of big O, if I have n vertices, how much space am I using? How much space? Oh. So I'll give you a hint. If I have n vertices, notice that how many entries are going to be in this matrix or 2D array? How many entries? If I give you n. It's quadratic. Yeah, exactly. It's n squared. So that's one thing you need to keep in mind. So yeah, if you look at the dimensions of it. So I have n entries this way, n entries this way. If I ask how many, it's just the dimensions, right? I multiply those two together. Obviously, if you store more data in there, though, like if these edge objects contained a lot more than just simple constant number of variables, then it becomes something else. But that's a whole other discussion. But yeah, no. So adjacency. So one perk of adjacency matrices is checking, obviously, hence its name, checking for adjacencies. It's really nice for that. So if I want to check, so it takes constant time to check if an edge ij is in the graph. So it's really fast for looking things up for the graph. If I don't know adjacency, really fast at that. So one other thing I want to point out, because it will be relevant, highly relevant for us, is when we want to get all the incident edges. So if ever I want to get all the incident edges on a given vertex, does anybody see how I would determine all the incident edges? So if I look at a vertex, I want to know all of the edges incident on a given vertex. How would I do that in an adjacency matrix? Any ideas? I'll give you a hint. Remember, I know everything about the adjacencies of the vertices from our matrix, or sorry, our two-dimensional array or table. So what would be one way I could do this? If I want to know, if I want to like list out all of the edges that are incident on a given vertex. Yeah, if I want to know how many there are, yes, I could just simply go across a row or go across the columns. Or I could read down a column if I would like. But it's easy enough to just go, okay, I'm just going to examine, like if I'm looking at vertex 0, I could just scan across this way. I could figure out which edges are incident on a given vertex, or I could even count how many there are, right? I just scan across a row. But how long does that take? So I'll give you a hint. Remember the dimensions of this array. Yeah, because there's n elements, exactly. It takes big O of n time. So it takes big O of n time to determine all the edges incident on a vertex. And I'll just remind you that it's just check a row. It's just check a row. That's relevant for you. But yeah, no. So those are the main things. I did include some remarks about insertions and deletions of vertices and insertion and removal of edges. I will warn you in advance that both these representations sort of take a bit of a hit if you wanted to do a lot of modifications to the graph. Now, insertions of edges is really nice in an adjacency matrix, or removals. Does anybody see how I can remove or include an edge in the graph? Does anyone have any ideas of how I could do that with an adjacency matrix? So if I wanted to insert a new edge into the graph, are any ideas of how I could do that and how long that would take? I'll tell you, it's a feature of this data structure. So remember, you know everything about the adjacencies. So if I give you an edge, ij like this, how can I insert that into the graph? Yeah, all you have to do is you index into the 2D, my 2D array, I index in there and I just set it to be 1 instead of just leaving it as a 0, right? I have direct access to that. Now, if we want to be very particular about it, because we're talking about undirected graphs, you would have to assign it both directions. So you'd have to do ij, then ji, and assign that to be 1. But keep in mind, if you're doing things with directed graphs, you just have only where it's just one direction, right? Because it's a directed edge as opposed to an undirected edge where it can kind of go both ways. But yeah, no, so you can do insertions or removals of edges very efficiently in an adjacency matrix. However, the big but with this data structure, and most of these have this problem, is that if you want to insert or remove a vertex, do you see how intimately that would cause problems with our 2D array? If I want to create a brand new vertex I want to put into my data structure here. So notice that everything is tailored around there being n vertices, right? So you would have to make some practical considerations for dealing with that. One other problem you're going to run into, so as a consequence of this, is that you'll notice that I have a lot of zeros sometimes in these tables. So some people will implement these tables or arrays instead as link structures called sparse matrices. So if you're curious about that, they're called sparse matrices. But that's I'm not going to be covering those. Essentially, it's a big linked structure similar to a whole bunch of linked lists. And instead of having where they're right beside each other, you essentially have a big net of nodes akin to having a whole bunch of linked lists connected to each other, like a grid. So you can eliminate a lot of these zeros by just doing that. That's one way you can optimize a little further if you have a really big graph. But as somebody else pointed out, that for undirected graphs, the matrix A is symmetric. So I just felt like I wanted to acknowledge that, because believe me, if you have one of these and you're writing this out, it's a very helpful thing to know, especially if you're, say, doing some automated process. You know that only certain parts of this thing actually matter, right? So in practice, you might just completely ignore the lower triangle, for example, if you don't never use it. So that's something to be, I guess, versed enough to know about. But, like I said, this could have many, many zeros in it, meaning you're wasting a lot of space. So that's a big drawback. So one thing we can do is try to resolve that by trying to incorporate more information about what my neighbors or incident edges are. So that brings me to the second representation I want to talk about, the so-called adjacency list. So the adjacency list is one natural way of resolving this problem. So adjacency matrices are great for dense graphs. So graphs with lots and lots of edges. They're great for when the graph has lots and lots of edges because you're not wasting space. So these are great for dense graphs. So remember, so when I mean dense graphs, I mean like the number of edges is something like big O of n squared. Where you have many, so it's something approaching that. Usually an adjacency matrix would be quite nice for that. Now, what if I had, say, for example, only a linear number of edges? Say it's big O of n instead of n squared. Notice that there might be a lot of zeros in there, and that's a problem. So here's the other representation I want to show you. It's called an adjacency list. So What is that? So instead of having it where I store a whole bunch of zeros, for example, what I'm going to do is I want to consider the incident edges. So I want to, instead of storing just, oh, they're just their adjacencies, I'm going to store, if there's an incident edge, I want to store only that information. This is why we call it an adjacency list, is I only want to know the vertices that are adjacent to my vertex. That's it. So what is an adjacency list? It's an incidence sequence for each vertex. Where there is a collection of incident edges for vertex V. So, you might ask, Dan, what does that mean? So, I deliberately use the word collection because when I show you the more generalized version, it'll be very easy to swap different data structures out for how you store these incident sequences. So I'm going to first show you the classic version. And believe it or not, a picture will be sufficient for me to describe it to you. It's actually not very bad at all. In fact, it's quite natural once you recall your ideas back from, say, talk about linked lists. In fact, you may have seen this idea before if you thought about maybe hashing or separate chaining. If you've ever seen this concept from maybe 210. I'm going to use something very similar as a setup for this. So what I'm going to do, so for the classic version, is it's going to be a vertex indexed array where each element is a linked list and vertices are indexed 0 to n minus 1. So just as a remark, because if you're using a directed graph, note in a digraph, if I have a vertex going from U to V, means put V in the adjacency list of U. So what's going to happen is I'm going to be maintaining some collections of lists. I use that word explicitly. But in the most classic version, I just use linked lists. It's very nice and simple. So for example, if I take that other graph, actually, why don't we go over there, and I'm going to draw it over there because I'm going to use the same exact graph. So let's head over there. Let's head on down. I'm just going to kind of do a pseudo dance as I walk over here. It makes the penguins cry, okay? I don't know why I just said that. It makes things fun on a Thursday. And the potential is just unending. I have no idea, like I said, why I said that. It makes things fun. So, anyways, I'm going to use the same exact setup here. So now I'm going to label each one. So I'm going to have 5 vertices, so I'm going to have 5 linked lists. So I'm going to have 1 for 0, 1, 2, 3, 4. And what I'm going to do is I'm going to maintain a linked list. So each of these is going to be a head of a linked list. So you know how you have a single linked list, you'll have the head of the linked list? You're going to store each one of these is going to be a head of a linked list. So for example here, I would store the opposing endpoint. And then I would say that there are no other elements, right? Because I only have vertex 4 that's adjacent to vertex 0. So I only store its opposing endpoint. I may store some additional data with that. For example, it may store a reference to the edge object. That's very common in practice. For list indexed at 1, well, I know which vertices are adjacent to vertex 1, 2, and 3, right? So I'm just going to put 2, 3, null. Then I have 2, vertex 2, I think it just has 1 and 3 as their neighbors. So I have 1 and 3. And then I have, for vertex 3, I have 1, 2, because I have 1, 2, and 4, right? And then, of course, I have for the final one, for vertex 4, I should just have 2. I should have vertex 0 as the opposing endpoint, and vertex 3. So if you've seen this, you'd be like, okay, I could probably implement that, right? It's pretty natural. If you look at it, it's just a list. It's an array full of linked lists, and each node just stores the edge information or the opposing endpoint. If you want to be very classic or pure about it, it just stores the other endpoint. But usually in practice, you could include a reference to the edge object. Reference or pointer, however terminology you would like to use. But yeah, that's a very natural way of using a linked list in terms of the adjacency list. Now, so that's how you would represent it classically. Here's the generalized version. So instead of doing it this way, I'm going to store a list of vertices. So some collection of vertices. Actually, I'm going to be much more. Let's see. We're going to have so this one V is going to be a primary data structure. So a primary data structure. So this will be something that you'll have off to the side that will store information for indexing from a given object. So for each one of these, we'll have a pointer to some vertex object. So V0, V1, V2, V3, V4. And in here, you're going to have a secondary data structure. For each one of the vertices, you're going to have a pointer to some collection that stores all of the incident edges. DE, CD, E, C, B. Let me fix that E here. It's a little sad there. ECB. And we have AB. So each of these is a secondary data structure. So some collection. So I must stress that in this generalized form, you have control over these data structures. So if you want to use hashing, for example, you could use hashing. If you want to use a map, in the most broadest sense, like for hashing, you could do that with this. If you want to swap out what these are stored as, like you want to make them into tree data structures, you could do that. I'm not stopping you. You could do that if you wanted to. It's very general. You could do it in this way, but usually I'll just refer to this classic version. But I want to expose you to some of these things so you can think about how you could take them and generalize them. So does anybody have any questions about these two here? So if I ever ask you about this, I'll only talk about this one. But I want to just show you that you could have a primary data structure that has it so you can index into each vertex object, which holds a pointer to a collection. And that collection will have all the incident edges. So this primary structure, for example, can be a map or a hash table. It could be whatever is most convenient for your practice. But each one sort of has, like, now you're talking about practical considerations for the data structures, right? That's more of something we talked about, say, for example, in a class like 210. So that's where this is sort of leaching into, if you're curious about that. So let's talk about how we could I just want to highlight a few small things. I wouldn't call them small, it's just that I only have a couple minutes to tell you about it. So first, you might ask about the space usage here, because that's obviously one very important thing. Last time I had a quadratic. Here it's a little bit different, believe it or not. I have a question for you. Notice, I want you to look at how many, so first, you know that you're going to have to store all these pointers here. There are exactly n of these, but how many nodes do I have in each one of these lists? How many do I have? I'll give you a hint. I talked about this concept last class, well, last lecture. So think about it. Each one of these lists represents how many incident edges there are, where they're just showing the other endpoint of the edge. So we have a name for this. It starts with a D. How many of them, how many incident edges there are is this thing. It starts with a D. I talked about handshakings before in this previous lecture of mine. I talked about shaking hands. Starts with a D, ends with a G, or an E, depending on if you're using the abbreviation or not. So I'll just say it. Notice that each one of these lists, it has the degree of a given vertex nodes. So you know that if I were to look at all of my lists here and I sum over all of these and asked how many nodes there are, there's actually an exact answer to this. And I showed you a very cute property in my last lecture. It's from this thing called the handshaking lemma. Remember, we were counting up how many handshakes happened in total versus those that actually happened in actuality between both parties. And we found out we were double counting the number of edges. So, what you could notice, each list has degree of V nodes, and there are lists for each vertex in the set of vertices. So, the total space used is big O of n plus the sum of all of the degrees of the vertices for all vertices. Does anybody remember what this is? What is that? What is that equal to? I told you it's a very cute property that pops up every once in a blue moon. And it's very useful to know, especially if you're playing with graphs. I will tell you, this is exactly equal to twice the number of edges. This comes from the handshaking lemma. This is exactly equal to 2 times m. So that means that the total space usage is n plus m. It's not quadratic, it's linear in the number of vertices and edges. So if you have a number of edges that's not too big, like it's big O of n, this is actually going to be linear in the number of vertices, which is much better. So anyways, I gotta stop right here. I'm gonna ask you to just take a quick peek at properties of adjacency lists. It's just on page 87. I want you to just take a quick peek at that. It's about half a page long. When we come back, we'll start talking about graph algorithms. So we'll start talking about how I can compute paths in graphs. We'll talk about how we can explore graphs. That's what we'll be focusing on next time. It'll be a lot of fun. So, that being said, I want to say thank you very much and have yourself a beautiful day. I'll see everybody later, okay?